Let's explore streaming algorithms, a specialized class of algorithms designed for processing data streams with limited memory. These algorithms are essential for handling massive datasets that cannot be stored in their entirety. A data stream is a continuous sequence of data elements that arrive at high speed. These streams must be processed with limited memory and computational resources. Think of it as a fire hose of information where you only get one chance to look at each piece. Streaming algorithms operate under specific constraints. First, they typically make only a single pass through the data, meaning each data point is read only once and in order. Second, they must perform real-time processing, handling elements as soon as they arrive without the luxury of storing them for later analysis. A key characteristic of streaming algorithms is their memory usage. The memory used must be sublinear in the stream length, meaning that as the stream grows, the memory consumption increases at a much slower rate. Ideally, memory usage should be on the order of big O of log n, or big O of square root of n, where n is the size of the input stream. Streaming algorithms are used to solve a variety of problems. These include frequency estimation to count occurrences of specific elements, identifying heavy hitters to find the most frequent elements, counting distinct elements to track unique items in the stream, and estimating quantiles to find medians and percentiles. The count-min sketch is a probabilistic data structure used for frequency estimation with a bounded error. The code initializes the sketch with d-hash functions and w counters. To update an element x, it is hashed using each of the d-hash functions, and the corresponding counters are increment. The HyperLogLog algorithm estimates cardinality, which is the number of distinct elements, using only big O of log n space. To process an element x, the algorithm hashes it, determines a bucket based on the hash, calculates the number of leading zeros in the hash, updates the bucket with the maximum number of zeros seen, and then estimates the cardinality based on the bucket values. Reservoir sampling maintains a random sample of k elements from a stream of unknown length. For the first k elements, they are added to the reservoir. After that, for each new element, a random number j is generated. If j is less than or equal to k, then the jth element in the reservoir is replaced with the new element from the stream. In streaming algorithms, there is often a trade-off between space or memory usage and accuracy. Using less memory typically results in lower accuracy, faster processing, and approximate results. Conversely, using more memory allows for higher accuracy, better guarantees, and more exact results. Streaming algorithms have many real-world applications, including network monitoring, social media analytics, database systems, and handling IoT sensor data. Key takeaways include understanding the trade-off between accuracy and space, the use of probabilistic guarantees, the need for single-pass processing, and the importance of sublinear memory usage. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.